Okay, we want to look at how we can use the STEAM tables to solve a question like this. Right, so we just want to get familiar with the STEAM table. And the question says that we should determine the state, that is compressed liquid, saturated liquid. It is saturated, but I can't give further details. Saturated vapor, mixture of vapor and liquid, superheated vapor of steam with the following properties. So before we get into the details of the question, let's get familiar with the steam tables, right? So we have tables not just for steam, we have tables for different compounds as well, for ammonia, for different kinds of refrigerants. One of the most common ones is the steam table. Now with the steam table, you realize that there are three different tables. So we have the one for saturated water, we have one for superheated steam, so that's here, superheated water or steam. Then we have one for compressed water, so that's down here, compressed liquid water, right? And you remember from our phase diagrams that we can have water, or we can have our substances in these three conditions. You can have a point where it is superheated, where it is compressed, and where it is saturated. So these tables help us to determine certain values of our substances based on the region they are in, whether they are in a saturated region, a superheated region, or a compressed region. It can also help us even determine whether what we have is saturated, superheated, or even compressed. So we'll start with the saturated part of our steam tables. When you look at the steam tables, the first two columns, right, usually we have either temperature or pressure starting. For the first two columns, it gives us the temperature and its corresponding saturation pressure, or it can give us the pressure and its corresponding saturation temperature. Saturation pressure just means the pressure at which your system is saturated. So if I'm at 5 degrees Celsius, I need a pressure of 0.8725 kilopascal for my system to be saturated. Saturated meaning that if it's a liquid, it's at the verge of becoming a vapor. If it's a vapor, it's at the verge of becoming a liquid. And if it's or it can be a vapor liquid mixture. So it's these three things. It's either we have a liquid becoming a vapor, or liquid at a point that it can just become a vapor at a point that it can just start to become a liquid, or we have a combination of liquid and vapor coexisting. Then what we have is saturated. So at a temperature of 5 degrees Celsius, I need this pressure for those conditions to be fulfilled. In the same way, I can work from the pressure side. So maybe at a pressure of 800 kilopascal, the temperature I need in order for my system to be saturated is 170.41 degrees Celsius. Now, aside the temperatures and the pressures, we can read other properties. So we can read specific volume, internal energy, enthalpy, and entropy. So if we see any property with the subscript F, it's for liquids. The subscript G, it's for gases. So if I see something like this at 5 degrees Celsius and a saturation pressure of 0.8725, if I read this value, this is the specific volume of the saturated liquid. So if I consider a liquid that can just become a vapor, then this is going to be a specific volume of that liquid at that condition. And if I'm considering a vapor at those conditions that can just become a liquid, then I would have this value instead as my specific volume. So this value here means the internal energy of the saturated liquid. This is the internal energy of the saturated vapor. UFG is just the difference between them, so it's UG minus UF, right? HF is the internal energy of the saturated liquid. Hg is the internal energy of the saturated vapor. This is the entropy of the saturated liquid and the entropy of the saturated vapor. Whenever you read from these tables, please pay attention to the units. So the units from this table is in kilojoule per kilogram. So when you're using it for your calculation, keep it in mind that it is specific, right? They are kilojoule per kilogram Kelvin, or meter cube per kilogram. They are specific. Now, aside the saturated part, we said we have the superheated part. Superheated means that you are above the saturation point, right? So I think, let me open, I think I already had, let me open these slides and show us what I mean by that. So we spoke about this some time back, but we are saying that when we start out in this region, we are compressed liquid, right? We can increase the temperature to a point. So let's say, let me do it this way instead. So I'm at point one, right? I'm a compressed liquid. I increase the temperature till I get to point two. When I get to point two, I'm a liquid, but I'm at the point where I can now start becoming a vapor. So I become a saturated liquid at that point. So from point two, I now start becoming a vapor, becoming a vapor. So I'm a mixture of liquid and vapor. There's a part of me that is liquid, there's a part of me that is vapor. So more vapor will be formed until I get to point four. When I get to point four, all the liquid would have changed to vapor, right? Now I'm a saturated vapor. I'm at the point where I can now go back and become a liquid. So if we're moving in the reverse direction, I'm a vapor at this point, but I can go back and become a liquid. So I'm at that verge where I can easily go back and become a liquid. Then above it, I become super heated. So I'm just continuing to increase the temperature above its saturation point. So you realize that from point 2, point 3, and point 4, they are all at the same temperature. So at the saturation point, the temperature and the pressure are always constant. So you can have a saturated liquid at that temperature and pressure, a saturated vapor at that temperature and pressure, or a mixture at that temperature and pressure, right? But the moment you go above the saturation point, you become superheated. The moment you go below the saturation point, you become compressed. Okay, so to let's get back to our discussion on the steam table. So if we just look at the superheated part of the steam table, you realize that the superheated part, let's say at P equal to 0.01 megapascal, they will still give you the saturation temperature. So you know the temperature at which it will be saturated. And then they give you the temperatures above the saturation temperature now. So if you think about it, if I have a system at a particular temperature and it's saturated, and I should increase the temperature, I'm adding more heat. So I'm going to make it move above the saturation temperature. It's going to become a superheated vapor. So here I have 45.81 degrees Celsius. That's at the saturation point. Then I have these values here. So this is now superheated. So if I check maybe the enthalpy of water at 0.01 megapascal, right, and then I check at 150 degrees Celsius, I'll be getting 2783. That's the enthalpy of the superheated steam. It's no longer saturated, it's superheated at these conditions, 0.01 megapascal and 150 degrees Celsius. Then again, we also have the compressed part of the steam table. So for the compressed part, the same understanding. We have a pressure. They show us the saturation temperature in the bracket, right? But all the temperatures are lower than that. So let's think about this once again. If I have a system at a particular temperature and I should drop the temperature, I'm forcing the molecules to move closer together. So it's going to become a compressed liquid instead. So something like at 20 degrees Celsius and 5 megapascal, if I read an enthalpy value of 88.61, I know that it's a compressed liquid or it's compressed water. But we don't really work so much with compressed liquid water. Okay, it's good to know it, but then we don't really, usually it's steam and saturated water that we work with. So let's look at the tutorial questions. It says that we should determine the state, right? Whether it's compressed liquid, saturated liquid, is saturated, but we can't give details. It's a saturated vapor, or it's a mixture of vapor and liquid, or it's a saturated, or it's a superheated vapor. So we have T at 120 degrees Celsius and a pressure of 101.4 kilopascal. For these things, you would need at least two properties to be able to determine every other property. So when you have a pure substance, right, and you are considering it in all its you're considering its phases as well. You just need two properties to determine everything else you need. So here I know the temperature, I know the pressure, I can determine whether it's saturated, it's compressed, I can determine the enthalpy, internal energy, all those things. So I think before I get into the tables, let me give just a little side note so that we apply it to what we are doing. So if we are at a given temperature, the pressure that we read from the saturated steam table is the saturation pressure. If our pressure is more than the saturation pressure, then we are a compressed liquid. So let's imagine water at 100 degrees Celsius and at 1 atm, right? It can easily become Yes, so let's imagine, so I was saying, let's imagine water at 100 degrees Celsius and then at 1 atm. You know that the water can start to become a vapor, right? Or we can even imagine the same thing as steam at 100 degrees Celsius and 1 atm. So as I was saying that from the um, phase diagram, we can have saturated liquid, saturated vapor in a mixture at the same temperature and at the same pressure. So we can have water at 100 degrees Celsius and 1 atm. It can start to become a vapor. Or we can have steam at the same 100 degrees Celsius and the same 1 atm, right? And it can start to become a liquid if we work on it. So if we have just water at 100 degrees Celsius and at 1 atm, and I compress it, I increase the pressure. I'm compressing it, I'm pushing the molecules together, so it becomes a compressed liquid, right? So if I'm at a saturation point and I increase pressure, because I'm pushing the molecules together, I become compressed. So if my pressure is more than the saturation pressure, it's a compressed liquid. But now if I reduce the pressure instead, I'm reducing how much force I'm putting on the molecules. So I'm not pushing them together as much as um, is necessary in order to keep it saturated. So the molecules can start to escape. So the moment my pressure becomes less than my saturation pressure, and it becomes a superheated vapor. But when it is equal to the saturation pressure, then it is saturated. Now for the temperature, it works with a very similar understanding, but temperature works um, quite opposite to pressure. So with temperature, if once again I have water 100 degrees Celsius, 1 atm, and I increase the temperature, you realize I'm giving more energy to the molecules. So the molecules can start to escape more, right? So I'll start getting more vapor. So if I increase the temperature, I'm going to get superheated vapor because I am adding more energy to cause the molecules to escape more. But if I should decrease the temperature, what is going to happen is that I'm pushing the molecules closer together. So they're going to become a compressed liquid because I'm decreasing temperature, I'm reducing their energy. The molecules are getting closer together, it becomes a compressed liquid. If T is equal to T sats, then that one is just saturated. Now for any property, whether it is enthalpy, entropy, internal energy, specific volume, remember I said F is for liquid and G is for gases. So if M is less than MF, I'm a compressed liquid, right? MF is the property of the saturated liquid. So if I am less than the saturated liquid's property, then I am a compressed liquid. But if I am equal to MF, then I am saturated. If I am more than the value for Mg, right, then I am more than the value for when it is a saturated vapor. So I'm a superheated vapor. So just keep this in mind. Superheated vapor is above saturated vapor. Compressed liquid is below saturated liquid. So here we see that the property is below the value for saturated liquid, so it's compressed liquid. And here we see the value is above the property for for saturated vapor, so it is superheated vapor. If I am in between, then I'm a vapor liquid mixture, right? So that is just something to take note of. So for the tutorials, 120 degrees Celsius, 101.42 kilo Pascal. If you look for 120 degrees Celsius from just the saturated part of the steam table, so that's here, 120 is here. The corresponding pressure is 198.67, but the pressure in question is 101.42. So remember, our pressure is more than the pressure required to keep it saturated. So we are pushing the molecules closer. It's going to become a compressed liquid. We can also read this from the side of the pressure instead of the temperature. So let's go to 101.4 kilopascal. Realize from the table that we don't have a value for 101.4 kilopascal, but I have 101.325. It's quite close, right? So for the sake of this analysis, we would use that, but ideally we are supposed to do what we call interpolation. So I'll make a separate video and teach us how to do interpolation, right? But just for the sake of understanding what I'm trying to say, let's assume we are working with 101.325 kilopascal instead. Now that the temperature is 99.97, but the temperature given to us was 120, right? So if I'm supposed to be at 99.97 to be saturated, and I'm adding more energy by increasing the temperature, then I'm going to become superheated because I'm causing the molecules to move further away, right? Um, yes. So from the question we have, oh, okay. Sorry, so I made a mistake earlier when I said it was compressed. It was superheated. So I'll re-explain it from that angle, right? So what I'm trying to say is that at 101.3 kilopascal, if you're working with 99.97 and we are using a temperature of 120, which is more, then we are going to become superheated. Then from the temperature side instead, right? So I'll just take it again. Sorry for the mix-up. At the temperature side, the question is saying that we have 198.67. So that's what would make it saturated. But our pressure is less than that. Our pressure is 101.42. It's not more than, it's less than. So if I need 198.67 to hold the molecules together to make it saturated, and I drop the pressure, I'm causing the molecules to escape, right? I'm causing molecules to be more free because I've reduced how much pressure I'm putting on them. So it becomes superheated instead, right? So sorry for the mix-up. So it's just with what we are saying here. Our P, right, from the question is less than the P sat from the table. So it's superheated vapor. In the same way, our T from the question was more than the T sat from the table. So it's a superheated vapor. Now, if we should consider B, 210 degrees Celsius, 1907.7 kilopascal, you realize that if I come to 210 degrees Celsius, that is here, 210, the saturation pressure is 1907.7. So it's already a saturated condition. So we know it's saturated. But do we know whether it's saturated liquid, saturated vapor, or a mixture? We can't tell. We don't have enough information to be able to tell what it is. We just know that it's saturated. But remember that we said if it's saturated, it can be liquid changing to vapor, vapor changing to liquid, or a combination of vapor and liquid. Because this is all we have, we can't determine whether it's going to be liquid, saturated liquid, or saturated vapor, but we know that it is saturated. So the answer is going to be it is saturated, but I can't give further details. If maybe we had an idea of maybe the VF or the VG or the U value or something, we'll be able to tell that okay, it's a liquid, oh, it's a vapor, it's a mixture, but we don't have that. Right? So we can't say anything further aside from the fact that it is saturated. Then we have another question here. T at 100 degrees Celsius and 2000 kilojoule per kilogram. So back to the steam table. If we come to 100 degrees Celsius, it's over here. So let me extend this so that we can consider our enthalpy values as well, because we are looking at enthalpy as well, 2000 kilojoule per kilogram. So our enthalpy values are here, and then here, the end here. So I can enlarge this now. We know the values we are working with. So this is going to be for HF if it is a liquid, right? The enthalpy will be 419.17. If we had the 100 degrees Celsius and 419.17, we know that it is a saturated liquid. If we had 2675.6, this is for the saturated vapor. But our answer is 2000, it's in between. And remember we said that if our answer is in between, right, this last point down here is going to be a vapor liquid mixture. So it means this is going to be a vapor liquid mixture. 2000 is in between 4.19 and then 2675.6 kilojoule per kilogram. So it's going to be a vapor liquid mixture, right? Then the next part of the question says P at 101.42 kilopascal and V at 1.6720 meter cube per kilogram. So let's go to the pressure side of the table, and then we still don't have 101.42, so we'll just approximate as 101.3, right, for now. 101.4 is actually going to be very close to this, so it wouldn't be too much of a problem. Okay, now we are looking at the specific volume of 1.6720, but if we check our tables, this is the specific volume. So this is the specific volume up here for the liquid and for the vapor. So this value here is for the liquid, and then this value here is going to be for the vapor. Now the answer we are looking for is 1.6720. 1.6720 is in between those two values. So it means that it's also going to be a mixture of vapor and of liquid. Okay. So that's if we were using a 101.325, right? As I said, I'll show us how to do interpolation later so that we can be a little bit more accurate. But then the value is going to be in between these two values. Now let's look at the next one, T being equal to 60 degrees Celsius and U being equal to 2762.4. So we'll come back to the temperature part. T is equal to 60 degrees Celsius, so that's here. I'll just extend it. Let me clean the previous ones. Okay, and then we have our u values. So the u values are from here, and they end here. Now the u values we are getting, this one is saying is 2762.4 kilojoule per kilogram. If we check it, 2762.4, 27 is above the saturation vapor, right? So it means you're going to be superheated vapor, because we said that if we are saturated, if we are above the saturated vapor, then we are superheated vapor. So if our property, right, is above the value for the saturated vapor, then we are superheated vapor. And if we check it, we have 2762.4. That is above the UG value, 2455.9. So it's above the value when it is a saturated vapor. So it's going to be a superheated vapor. And the last one is 60 degrees Celsius and 101.42 kPa. So at 60 degrees Celsius, the pressure that we are seeing is 19.947 kPa. But the pressure that we are working with from the question is 101.42. This is more than the pressure that will keep it saturated. So let's think about it. If the pressure that will keep it saturated is 19.947 and I'm increasing the pressure, it means I'm pushing the molecules closer together, right? So that would make it compressed. The molecules are not going to escape, so they are going to become compressed, and they are going to become a compressed liquid. So it means for the last one, we are going to have a compressed liquid. So this is just for reading from the steam table. We'll make a separate video later to explain the quality of steam, and then to show us how to do interpolation as well, in case we get a value that we don't see on the steam table. So let's assume we have 20 and we have 25, but we need a value of 23. We'll use interpolation because it's in between 20 and 25 to find our answer. So we'll make a separate video for that to show us how to go about it. Okay, thank you very much.